Hi, welcome to this video. I've been looking for a while now for a project that I can turn into a video. After a while, I have a hobby if you can't share it with anyone else. Hope you find this one interesting. It takes basic Arduino stuff you can order and combines it with some DIY electronics to make a prototype of a solar-powered, internet-controlled garden irrigation system. Once that's running, I'm going to convert the prototype into a standalone circuit board. So all of those devices and the custom electronics are going to become one device. The reason I'm doing this is I run into a few problems with garden irrigation controllers you can get at the hardware store. Those are things like this little box here. These retail between $40 and $60 in New Zealand, and they're not too bad for the price. It has a ball valve run by an electric motor and a couple of position switches to control the flow of water. The ball valve switches the water on and off slowly, and that has the side effect of not generating water hammers. Water hammers are those knocking sounds you hear in plumbing when you turn taps quickly on and off, and those are basically supersonic waves travelling back up the pipes. They cause a huge amount of damage, cause pipes to split, hoses to rupture, so they're best to avoid. And means one of the things that we'll have to put into the design as we go is probably something like pulse width modulation, so the valves are going to turn off slowly rather than suddenly slamming the valve shut and creating that water hammer. Now, this unit, like most of them, controls frequency and runtime. So you can set the frequency anything from an hour right up to a week. And runtime, that can go from 1 minute right up to 120 minutes. There's also an on setting, so if you're out in the garden you want to fill up a bucket of water or something like that, you can just select that setting and then switch that off again when you're finished. Now, they're pretty good and they're quite reliable, but I have found a few problems with them. One of the main ones is back here, where the casing has to take the full pressure of the water. Now, you might be able to see just in there that there are some weep holes in the casting, and what will happen after a while is possibly the plastic cracks internally. You just need to find water leaks coming out through those holes or around seams in the casting. And no matter if you put in new washers or tighten the hoses up, they still leak, and they do leak badly. So that seems to be a problem across a lot of manufacturers. The other thing I found is that some of the units tend to lose time. So you'll set the timer for a particular time during the day, and you'll find that creeps forward by a few minutes each day. And I have found some that will jump around several hours at a time, so that can be very frustrating and very annoying. The other thing I like to do is have more than one outlet. Now I do have a couple of these, but you know, $40 to $60 each, you're spending over $100 on two. The multi-outlet ones are probably $80 or $90 each. And you want your multi-outlets if you're going to be, say, watering different parts of the garden at different times. Tomatoes, for example, are less water tolerant, so you don't really want to have those on the same cycle as all the other plants in the section. The other problem too is, if you want to change the times, or you want to start your watering while you're away or something like that, you can't do it. Say you set the time, you want to go up from 5 minutes now and you want to start doing 15 minutes tomorrow. You actually have to be there in the morning when you want to do that. Now that's a real hassle. So want something where you can set the date and time and it will actually start from that. And also you can stop the cycle, say you're changing from summer to winter. So those are the sort of things I'd like to put into the new timer. And for the money I'm spending on these controllers, I should be able to build something that can do that. I've wanted to work on a solar powered project for a while now, so this unit will be run from a solar panel. To be fair, the batteries in the dumb controllers last 12 to 24 months, so I have no complaint there. I just want to run it on solar, and it means I can add more stuff to it later if I increase the battery capacity. Things like cameras, garden lights, etc. Practically anything you can use in the garden. The Arduino microcontroller will manage the power conversion from the solar cells into the batteries. I want the device to run at least 3 channels areas that can be set for different times. Off those I want to run small sub-channels run by the main channel, but allow some plants in that area to receive less water. For example, tomatoes need less water than other types of vegetables.
The main solenoids and sub-channel solenoids are shown on channel 1 at the top right. What will happen is that the main channel will come on, then a few minutes later the sub-channel will start. Finally they'll both shut off at the same time. The sub-channel may also be set to come on once every 2 times the main channel comes on, for example. The main solenoids are 1/2 inch and the sub-channel solenoids are 3 mm. They are for the smaller hoses that go to separate plants. In this way I will get more control over the water flow to each area of the garden. I want to be able to vary the basic watering program for each area based on the amount of sunlight, temperature, oil, soil moisture and the amount of rain that has fallen there. So it will be sensors monitoring all of these parameters. The rainfall sensor is the pivoting bucket design. This means the actual quantity of rain can be measured. Unlike some of the rain sensors made from PCBs with conductive strips, they can simply tell if it's been raining. A flow sensor and pressure sensor will allow the amount of water the sprinkler system is using to be logged so the cost to run can be calculated. Because there is a pressure sensor, the unit will be able to delay watering if home appliances or residents are using water. It will wait a few minutes and check if the pressure is normal before starting. If it is part way through irrigating when the pressure drops, it will pause until water pressure returns to normal before resuming. A real-time clock allows the watering cycles to be started and stopped on schedule. For example, I might be going away and I want the watering to start in 3 days' time at 6 AM. Or if we are transitioning from autumn to winter and I want the watering to stop at the end of April, the real-time clock also allows sensor readings and events to time-stamped. Once programmed via USB, which we use for programming and debugging, the unit will have its settings altered via the wireless connection. The user will be able to retrieve current settings and sensor data from the unit via a browser. The user will also be able to change irrigation settings on the unit and set real-time clock and date. Manual controls on the outside of the unit connected to each channel will allow water to be turned on and off manually if the user is in the garden and just wants to do some on-demand watering or fill up a bucket. You simply need to press the button to start water flowing. This mimics the function of the on switch on the original device. I am concerned you put a timeout on these to restrict the runtime in case something falls against the switch, or you have intruders in the garden who might want to leave your tap running. If it times out, you can press it again, or it may have the number of presses determine the number of minutes the water is on for. I've been testing and accumulating circuits and parts for this project over the past few months. Let's have a look at where I'm at and what more I need to do to get this project finished.
I put together a prototype which tests several of the subsystems included in the design. So far this includes the main parts of the design. It includes the 5-volt Arduino Nano. This form factor includes enough I/O for the job, and I hadn't decided when I started if I was simply going to solder one onto the board or incorporate it into the PCB. The DS3231 real-time clock connects via I2C. I was hoping to use the alarms on this to generate interrupts for the Nano, but there aren't enough for this purpose as I want to have 3 or more channels, which would have meant swapping them out. I may have a look at this again when doing the code for the scheduling. The other good thing about this module is that it has a thermometer, so the ambient conditions on the board can be measured. And these can be got quite reasonable prices. This one on Amazon, for example, it's going for about 50 cents. I think I paid about $3 for 5 of these, which is quite amazing. Once I had the basic test set up running, it was powered by the USB port, I built the 5-volt power supply. This is based on the LP2950, so I could test the conversion from 12 volts to run the Arduino. What you'll notice about this, if I unplug the USB port now, so the USB port is unplugged. It's now running through the 5 volt supply there. 12 volts is required, so that's what the solenoids run on. For most of 6 volt solenoids are not rated to stay open for an extended period, and in practice the 12 volts will be up to 13.6 volts at the battery. This will be tested when the solar converter circuit is included. The LP2950 is a 100 milliamp 5 volt switching power supply.
100 milliamps so far will be enough to run the real-time clock in the Nano. This is the circuit here. Using the LP2950 means that the 5 volt supply is a nice small form factor and it doesn't need any external inductors. I'm doing a full rundown on the power supplies and solar charging system in episode 2, where you'll also find out why I went with sealed lead acid batteries. Switching regulators have been chosen as they are more efficient in battery powered systems. They can be 3 to 4 times more efficient than linear regulation. Even though this is a solar powered unit, there may be weeks of bad weather and so every coulomb will count. The 3.3 volt circuit is also shown. That's on the LM2575T. That will supply 1 amp. The test circuit I've built is actually a 3 amp regulator. That's because I only had one of those available, but the final build will actually use the 1 amp version. You'll notice I'm using the Eagle for the schematics and later the board layout. It just makes it really easy. You can just lay everything out here, document it, put it in the video. The best thing of all, it's free. The capacitor and inductor values here may change later, as these are shown for the adjustable version of the LM2575T. So it's possible to optimize those to 3.3 volts. The circuit's based on the information in the component data sheets for each of the respective components. I'm just using the power jack point here just as a basic input source for the circuit, but eventually that will be the 18 volt supply from the solar panel.
This is the 3.3 volt supply. The inductor's hand wound. I tend to buy powder inductor cores where the turns per microhenry are specified. That way I have a ballpark figure for the turns required and I can fine tune with an inductance tester. At this stage only the ESP8266 wireless network module needs a 3.3 volt supply. This is the prototype board. The board is laid out with a 12 volt side on the left, the 5 volt side on the right. The 12 volt positive has its own bus. I'll put the breadboard schematics for these up later if anyone wants them. The tip 120 which I'm using to run the solenoids is an NPN Darlington transistor rated at 5 amps at 60 volts. These are made by a number of suppliers, but that's the data sheet for the Fairchild version of it. The tip 120 is quite overrated for the requirements here, but the TO220 package should dissipate enough heat without needing a heatsink. The solenoid valves that control the water for the system were sourced from eBay. I'm going for metal fittings where possible for UV resistance, as we have strong sun here under the ozone hole in New Zealand. The larger half-inch solenoid valve has its own built-in filter and a water-resistant cap. These go for about $6 on eBay. Smaller solenoids go for about $4. These are known as 12 volt pneumatic solenoid valve for gas, water, air, normally closed. They're also available as recycled from coffee machines for about $2 each, which were where I got these ones. The normally closed part is important, and these solenoid valves are available as normally open. With normally closed, the system fails to close if there is a problem.
This is the circuit to drive the tip 120. As the tip 120 doesn't have a built-in bypass diode, I've added a 1N4001 to protect the Darlington against the field collapse of the solenoid. Each channel in the sub-channel drive circuit will be implemented in the same way to increase flexibility on the sorts of devices that can be driven. Being able to add the Arduino Nano into EP8266 boards in Eagle makes the design process much more straightforward. I'll put a link to the library that enables you to do that in the explanation for this video. Okay, the code running on here at the moment is based on the Blink example code. It's just been copied pasted. I've added wire.h to allow communication over the I2C interface with the real-time clock. Specify the address of the device. There are some decimal to binary coded decimal conversions in there. That's because the clock accepts and sends data in binary coded decimal. got pin 3 set up for the LED, pin 10 for the solenoid, and we're initializing the wire library and the serial port for 9600 board. The rest of the code here is just the example code that comes with the real-time clock. Just sets up dates, retrieves the data, processes time, date, day of week, for example. All the loops doing here are setting the LED and the port with the solenoid on it high, waiting for 1 second, then setting them low. We're also displaying the time to the serial monitor just for a test, and we then have another delay and the cycle repeats again. So once I get on to actually developing the code for the irrigation system itself, we'll put a few objects in there to manage channels, put a loop in to monitor the timing in the absence of any interrupts. I'm not too sure yet exactly how the interrupts are going to work, but work that one out as I go.
This is an ESP8266. Well, actually it's an ESP8266 mounted to a small circuit board. These actually come in a number of form factors, which we'll have a look at in a minute. Now, when this first came out, everyone assumed it was simply another wireless module. You plug into Arduino, connects to the network, that's pretty much it. But it turns out, when people had a closer look, this is actually a 32-bit RISC MCU, and it's running at 80 megahertz. Not only that, it has a full TCP IP stack, pretty good general purpose input-output, and a couple of other little items that make it very interesting.
As well as the ESP01, which I'm using here, there are over 14 different form factors available for this module. The main variation is the antenna or lack of it, and a number of breakouts for the IC package. Those with more pins expose the input-output capability of the IC and enable it to act as a standalone MCU if required. As you can see here, there are quite a few of them, and obviously horses for courses. Ones with slightly better antennas, you'll notice this one here, for example, can have an antenna extension. There are also ones available with small ceramic antennas, and ones which have a lot more pinouts available as part of the package. The ESP8266 can be used in several different ways. As well as acting as a TCP/IP stack, it can also act as a simple pass-through wireless adapter. The manufacturer, ExpressIF, makes 2 sets of firmware. The ExpressIF SDK and also a real-time stack or a real-time operating system, which basically optimizes real-time capabilities with interrupts and callbacks. Additionally, there is a package known as Node MCU, which supports a Lua interpreter natively on the MCU. It provides a slightly more user-friendly IDE. This is based on the ESP12E package, although the Lua code can be installed on the normal form factor as well. This has a reputation as a resource hog, especially from a memory point of view, but it is possible to upgrade memory on the unit up to 4 megabytes from what is usually 512 KB. The device can be programmed standalone via serial communication via an FTDI adapter or through its associated Arduino using the Arduino IDE. This diagram shows the connection through the Nano. The ESP8266 is a 3.3 volt device. This means that as well as supplying 3.3 volts to VCC and other pins, the RxD incoming data pin must have incoming signals converted to 3.3 volts. The TX pin sending data to the Nano is OK, as 3.3 volts is treated as data high. While I've chosen to implement this with the resistor voltage divider as shown, level shifters are available, and these can be bidirectional, which isn't required in this case. This is an example of one of the level shifters here. This is manufactured by Adafruit. It's a 4-channel bidirectional logic level converter. That means in a situation where there's a line which has signals travelling in both directions, this will handle the conversion for you. There are a number of options using logic gates and other things as well.
I've installed the ESP8266 at this stage as it's the key communication interface, and unlike the sensors, will determine the structure of the code to drive the system. I've moved a 3.3 volt supply onto the same breadboard. This includes the 10K pull-up resistor for the chip select line and the voltage divider for the RxD. I've moved the TRX and RDX pins to D6 and D7 on the Nano. The serial interface on the Nano is not used, so the serial monitor can be used for debugging and data transmission. The red LED indicates that the device is connected and on, and blue light indicates data transmission, for example when one of the AT commands is run.
The AT commands are run from the serial monitor, and the responses are also received there. This command will reset the device, for example. Another one will enable us to change the mode. Change the device into mode 3. In theory, this command should tell us which networks are available in a local area. That seems to be a little bit unreliable sometimes. Like now, for example, which is quite frustrating. Let's try another reset. Okay. And try once more. No luck there at all. This command will check the current firmware version. The AT plus CWLAP command will display all of the networks in the local area.
Setting the RCW mode to 3 turns the ESP into a wireless access point. That makes it show up on this list of networks on the Kindle that I'm looking at. It should pop up any second now, and there it is. And that just proves it's transmitting. It's a good way of just testing to make sure that there is actually something going on. In fact, clicking on the item will actually allow you to connect to it. Not too sure exactly what I can do from here with the Kindle, but I'll give it a go.
Well, finally got that network node display command to work, but it does show that the antenna on those is quite sensitive. I've ordered some other form factors to see if that helps. Perhaps an external aerial or something else may help. Most of the videos I've seen now, it seems to be pretty good, so I don't know exactly what's going on there. In episode 3 though, we'll be having a look at coding for the ESP2866 in more detail and get it connected up to the irrigation system. Well, that's all for this episode. You might notice the background picture. In episode 2 we'll go over the solar converter in a little more detail and where the design I've chosen came from and why I chose it. It's going to be based on the PWM5 solar charger. This design was originally a commercial design which has been open sourced by Julian Ilett, whose channel is subscribed from Randomstuffbot. Please go over there and have a look at some of his videos. He does excellent videos on solar charging, MPPT on solar charging, and also a whole lot of mailbags where he just gets random stuff from Chinese suppliers and has a look through them. They're pretty good actually. Well worth a look. Also coming up in episode 2 we'll have a look at different ways to charge a battery and how I selected the sealed lead acid batteries for the job. Then we'll examine the most efficient way of charging a battery from a voltaic cell, MPPT, and why I'm not using it for now. Thanks for watching.